Okay, so good afternoon to all and welcome to lecture number 12 of control system. In the previous lecture, we talked about the translational mechanical system and then how to obtain the transfer function of that translational mechanical system. So that we have studied by applying the Newton's law and so on. Now we'll see some more examples on that one, and also we'll see how to obtain the nodal diagram, which will make the problem simpler, and then we can easily find out the transfer function of translational mechanical system. So suppose, for example, consider this system. Okay, so you know that in the translational mechanical system, there are three basic elements. One is mass element, another one is dashpot, and a third one is the spring element. Coefficient of this mass element is M, coefficient of dashpot element is B here, then K is the coefficient of spring element, right? When you apply a force on this system, so definitely there will be opposing force offered by this mass element, which is directly proportional to the acceleration. Also, there will be a opposite force offered by this dashpot element, which is directly proportional to the velocity, and then there will be also opposite force offered by this spring element, which is directly proportional to the displacement. So where x is the displacement, and we know the relation between velocity and displacement. If you take the derivative of displacement, that is nothing but the velocity. If you take the derivative of velocity, that is nothing but the acceleration, right? So if you draw the free body diagram, and if somebody asks you to draw, okay, find out the transfer function of this mechanical system, then how to find out that one? So first, you can draw the free body diagram. So on this mass element, there will be a force which is applied F. So F is, suppose for example, if it is in this direction, okay, so definitely there will be opposite force offered by this mass element, so it will be opposite to the applied force. Fm is the mass force of reactive force offered by this mass element. Similarly, reactive force offered by this dashpot element will be Fv, and then reactive force offered by this spring element will be Fk, which is opposite to the this one. So you know that as per the rules, total incoming force must be equal to total outgoing force. So this is basically the incoming force, and this will be the outgoing force. So F will be equal to this Fk plus Fm plus Fb. And you know that this Fk is nothing but the force offered by the spring element, which is directly proportional to the displacement, and the proportionality constant is nothing but the K. Whereas Fm is the force offered by this mass element, which is directly proportional to the acceleration, so m into d2 x by dt square, and then Fb is nothing but the force offered by reactive force offered by the dashpot element, which is directly proportional to the velocity. So F is equal to, in terms of displacement, it will be b into dx by dt. And if you take the Laplace transform, and finally if you find out the transfer function, where output is basically the displacement and input is nothing but the applied force. So Laplace transform output variable to the Laplace transform input variable is nothing but the transfer function. So x of s by f of s is equal to 1 by ms square plus bs plus k. So this will be the transfer function of this system. Now, whatever the examples we have studied, all those examples are really simple examples. But if there are a complicated or bigger examples are there, then how to solve this problem of mechanical systems and so on? So it will be a bit difficult. So for that, we have to draw the nodal diagram, and for that nodal diagram, there are some certain rules. So these are 4 rules with which we can draw the nodal diagram. And then once you draw the nodal diagram, then you can apply force equilibrium equation at every node, and then overall you can find out the transfer function by identifying what is the output and what is the input. Okay, so which are the steps involved for modeling? First thing is that we have to identify the displacement, whether now displacement may be a linear displacement or it may be the angular displacement. So linear displacement is represented with x and angular displacement is represented with theta and so on. So how many displacement points are there? So that you have to identify from the given problem. So identify various displacement from the equilibrium position in the mechanical system. So that you have to identify first. in the given mechanical system, how many displacement points are there. So number of displacement point will be equal to number of nodes. So each displacement point corresponds to a node in a mechanical network. So see that you might have seen in electronics or electrical circuit, you might have seen this one nodal diagram or nodal this one circuit diagram where like for example, resistance, inductor, and capacitor are connected together, so which forms the junction, and that junction is nothing but the node. And so like that way, there may be in the circuit, there may be 2, 3 nodes, 2 or 3 or 4 nodes may be there, and you know that we apply KCL there at every node, like total incoming current must be equal to total outgoing current, and then we try to find out the current flowing through each branch and so on. So here also we can draw the nodal diagram of a given mechanical system. So for that, okay, what we have to do, first thing is that for drawing the nodal diagram, you must know how many nodes are there. So number of nodes will be equal to number of displacement points. So how many displacement points are given in the problem, that you have to identify, and then that you have to mark as a node in the nodal diagram. And one more, you have to take the common node, that is nothing but the ground. So one more node will be the common node. So see that here, identify the various displacement point, whether it displacement may be linear or angular from the equilibrium position in a mechanical system, and then each displacement corresponds to a node in a mechanical network. So okay, each displacement point is considered as one node in a mechanical network, right? So all the points on a rigid mass are considered as a same node, and one terminal of mass is always connected to the ground. See that when you are connecting the mass element in this nodal diagram, so always one end of the mass is connected to the ground and another end is connected to the nearest displacement point. See that when you are connecting the mass, one end of that mass is always connected to the ground and other end is connected to the nearest displacement point. So reason is being the velocity or displacement of mass is always referred to the earth. So that's why one end of the mass element is always connected to the ground and another end of mass element is connected to the nearest displacement point. So I hope that from this first point, there are two things. One is you have to identify how many displacement points are there, okay, and number of displacement point is equal to number of nodes in the diagram, right? Then second thing which I told from the first point is that, okay, in case of mass, like for example, in mechanical diagram or mechanical system, there is a mass element, there is a dashpot element, and then there is a spring element or like that. So how you are going to connect the mass element in the network diagram of mechanical system, so nodal diagram of the mechanical system. So you know that there are two ends of this mass element. So one end of this mass element is always connected to the ground and another end of mass is always connected to the nearest displacement point. So in that way, you have to connect the mass element. So reason is that being the velocity or displacement of a mass is always referred to the earth, right? So these two things you have to okay, understand from the first point. Second point is that draw mechanical network by connecting together terminals of elements which change the same displacement point. Like for example, there may be for x1 displacement points, okay, spring element may be connected, mass element may be connected, dashpot element is connected. So that will form one junction there, right? Then after that, so after drawing this one, the entire diagram, nodal diagram of mechanical system, you have to write the force equilibrium equation. That force equilibrium equation is nothing but total incoming force must be equal to total outgoing force. So we write the force, or okay, see, the force equilibrium equation will be there in the translational mechanical system, whereas torque equilibrium equation will be there in case of rotational mechanical system. So write a force or torque balance equation for each node by applying D'Alembert principle of mechanics. That D'Alembert principle of mechanics equates the algebraic sum of forces at a node to 0 in a mechanical network, and in analogous, okay, you know that when you are applying the KCL at the node, so you know that algebraic summation of the total current at the node will be always 0. Similarly, in the mechanical system, total incoming force must be equal to total outgoing force, or algebraic summation of the force must be equal to 0. So that is what this D-Embers principle, which we are going to use at every node. Like for example, there are two nodes. So how many nodal equations will be there? There will be two nodal equations. One will be associated with node 1 and another one will be associated with node 2 and so on. So what you have done, you have identified here basically number of displacement point. Second thing is that you have connected all the components according to the given situation, and then after that you have written either force equilibrium equation for translational mechanical system or torque equilibrium equation for rotational mechanical system, okay, by using total incoming force must be equal to total outgoing force. That is nothing but the D-Embers principle of mechanics, which equates the algebraic sum of the forces at node to be 0. Okay, so that you have to write. And then once you write the nodal equation, from that you have to identify or you have to find out the transfer function of given system. So you know that transfer function is related with your output Laplace, okay, output variable and input variable. So just you have to take the Laplace transform of that one, and then find out the ratio of Laplace transform output variable to the Laplace transform input variable. So that will give you the overall transfer function of a given system. So once again, I'll repeat it. Okay, what are the steps for or rules for drawing the nodal diagram? First thing is that in a given mechanical system, identify the number of basically displacement point. So okay, in the mechanical system, okay, in the problem they might have given how many displacement points are there. So number of displacement points will be equal to number of this one. Number of displacement point is equal to number of nodes in the diagram. Then after that, I told about this point, like, okay, as there are three elements in the translational mechanical system, that is mass element or dashpot element or spring element. So mass, there, okay, for every element there are two ends. So one end of mass is always connected to the ground and another end of mass is always connected to the this one. Nearest displacement point, whereas dashpot and this one spring, it depends upon the given situation how to connect. If it is one end of that dashpot and spring is connected to the reference line, then you have to connect that one to the ground and then other to the nearest displacement point. Otherwise, okay, it will be connected between two displacement points and so on. So like that way you have connected that all those elements, and then you have formed the nodal diagram. Once you know, okay, draw the nodal diagram of given mechanical system, next thing is that you have to write the nodal equation. And you know that in electrical system you write the nodal equation by using KCL, that is Kirchhoff's current law. So you know that Kirchhoff's current law is nothing but total incoming current must be equal to total outgoing current. In the same way, okay, in this one also you can write total incoming force must be equal to total outgoing force, okay, for every node. So you can write the nodal equations, and then from that you know that what is the input and what is the output. So find out the Laplace transform of that one and find out the ratio of Laplace transform output variable to Laplace transform input variable. So like that way you can find out overall transfer function from the given okay, of a given mechanical system by drawing the nodal diagram. This will be more clear, okay, when we take the problem and so on. I hope that you have understood little bit from the given explanation. Now see that, okay, we'll consider a simple mechanical system. Like for example, there is reference one is there, and the spring element of this is connected to this one, and then another end of spring is connected to the mass, and then another end of mass is connected to the dashpot, another end of mass is dashpot is connected to the this another second mass element, and then again this is connected to the spring, and then finally it is connected to the this one mass element having coefficient equal to 4. Here spring coefficient is equal to 5. Now where force is applied? Force is applied here basically. See that what is the magnitude of that force? That is equal to 10 Newton, right? And now here there are given three displacement points. So x1 is one displacement point, x2 is another displacement point, and x3 is third displacement point. Whereas 6 is the coefficient of this spring, 3 is the coefficient of this mass element, 7 is the coefficient of this first dashpot, then again 2 is the coefficient of this mass element, then spring element 5 coefficient, and then 4 is the mass coefficient, and so on. So like that way. Now, if you would like to, suppose for example, okay, first thing is that how to draw the nodal diagram of these given systems, so that you have to study. So what I told you that first you try to identify how many displacement points are given. So in this example, there are 3 displacement points. X1 is there, X2 is there, and X3 is there. So you have to draw 3 nodes, X1, X2, and X3. So X1, X2, and X3, these are the 3 nodes which we have drawn. Now, with X1, how many elements are associated? So one spring is associated, then mass is associated, and then this dashpot is also in between X1 and X2, right? So what we'll do when you are connecting this spring element and mass element to X1, so you know that one end of the spring element is connected to the ground. So we have considered this as a ground. So this 6 is connected between X1 and a ground. See that 6 is connected, spring having coefficient equal to 6 is connected. One end of this one is connected to the ground. So this is connected to the ground. And another end, see that this is to the nearest displacement point. So nearest displacement point is X1, right? Similarly, this mass element M, okay, having coefficient equal to 3. Now, as I told you that always this mass element, one end of this mass element is connected to the nearest displacement point. So this one end of this mass element is connected to the nearest displacement point, and another end is connected to the ground. So that is the rule, right? Then this dashpot is connected between X1 and X2, so having coefficient equal to 7. So see that this X1 and X2, this dashpot is connected, right? So between X1 and X2, this dashpot is connected. So this dashpot is between X1 and X2, having say coefficient 7. Similarly, at X2, there is a force, okay? So when you are applying the force in this direction, so definitely there will be opposite force offered by this element, and this element. So, okay, we'll see the direction of force later on. So this is the force direction. So this force element is of having 10 magnitude is connected to the one end of this force is connected to the ground, and another is connected to the X2 here because it is applied at the X2, right? So this force is connected between X2 and the ground. Similarly, this 2 is connected. See that always one end of this mass element will be connected to the ground, and another end is connected to the nearest displacement point. So nearest displacement point is X2. So I hope that you have understood which are the elements associated with X1, which are the elements associated with X2, and so on. Now see that this 5 spring element 5 is in between X2 and X3. So we have connected this 5 in between X2 and X3, and then finally for this is connected between, see that this is the mass element. So one end of this mass element will be always connected to the ground, and another end of this mass element is connected to the nearest displacement point, that is X3. I hope that you have understood how to draw the nodal diagram from the given mechanical system. So see that solution is that choose the displacement point X1, X2, X3. So this X1, X2, and X3, these are the displacement points. So we have chosen them as a node. So X1, X2, and X3, right? And then after that, connect all masses between ground and corresponding node. See that this 3 is associated with X1. So one end of 3 is connected to the this one. X1, and another one is connected to the ground. Then 2 is connected to the nearest displacement point X2, and another end is connected to this one. And then 4 is associated with basically X3. So one end of 4 is connected to X3, and then another end is connected to the ground. So now mass element is over. Then what about this one? Fit the mechanical elements interconnecting 2 nodes in the network. Okay, for example, B equal to 7. Between X1 and X2. See that X1 and X2 B 7 is connected, right? Connect the remaining elements between ground and corresponding node. So basically this 6 will be connected between ground and corresponding node. Then this one dashpot 2 is connected between ground and node X2. Dashpot this one, right? So 2 is basically here. Okay, so this is the overall diagram of nodal diagram of given problem. Now, Further, you have to apply the nodal equilibrium equation like total incoming. So before that, we have to identify, okay, the direction of force and so on. So, but here the purpose of this example was how to draw the nodal diagram from a given mechanical system. So this is the way we can draw. Now, next one is that, like for example, consider this following system and then draw the nodal diagram. So this is the example. Like this mass element is there and then dashpot element is there. One end of dashpot is connected to the reference. So this is nothing but the reference. So one end is connected to the reference, another one is connected to the mass element, and then one end of spring is connected to the mass element, and then another end force is applied on that one. So this is the displacement point x1 and this is the displacement point x2, right? So when you are drawing the network diagram, mechanical network diagram, you have to draw the nodes first. So how many nodes? That will be equal to number of displacement points. So here x1 is one displacement point and x2 is another displacement point. So x1 and x2 nodes are drawn. Then see that in this K is in between which displacement points? So the spring is in between x1 and x2. So that's why this spring is connected between x1 and x2. Similarly, this force, one end of this force is always connected to the ground and another is to the nearest displacement point. So this force is connected between x1 and the ground. And then see that this one. Mass element, as I said, that one end of this mass element is always connected to the nearest displacement point x2. So x2, one end of this mass element is connected to the x2 and another is connected to the ground. Similarly, see that this dashpot element, one end is connected to the ground. So this is connected to the ground and another end is to the nearest displacement point. So that is x2. So this is the nodal diagram of given problem. Okay, and then how? See that once you have drawn this nodal diagram, how to find out the nodal equation. So for nodal equation, you have to write the nodal force equilibrium equation. So if this is basically incoming force, there must be outgoing force, because this force, when you apply a force on this spring, so there will be opposite force in this direction and so on, right? So total incoming force must be equal to total outgoing force. So see that this nodal equation at node x1 will be equal to what? What is the force equation here? This is incoming force and this is the outgoing force. So outgoing force is between x1 and x2. So this force which is associated with spring, so this force, incoming force is F, and then outgoing force is a spring force, and this is given by F in K into x1 minus x2, because this higher force minus lower force. So K into x1 minus x2. This is the equation at node x1. Similarly, what will be the node equation at x2? This incoming force must be equal to this outgoing force. So what is the incoming force? K into x1 minus x2 will be incoming force, right? And then or here it is taken this side basically, okay, x2 minus x1. So but if you take the x1 minus x2, this will be this side, right? Then what is the force? This force, so that will be m into d2 x2 by dt square. So this is nothing but the m into d2 x2 by dt square. And then what is this force? So that will be could be into dx by dt, dx2 by dt. So this x2 dot is nothing but the velocity, x2 double dot is nothing but the acceleration which is associated with this one, and velocity is associated with this one. So this will be the nodal equation at node x2, and this is the nodal equation at node x1. I hope that you have understood how to draw the nodal equation. Right, now see that suppose for example this example is given and you have been asked that find out the transfer function x2s by f of s. Means here x2 of s is nothing but x2 is output and f of t or f of s here in Laplace domain is the input. So this is the input and this is the output, and you have been asked that okay, find out the transfer function of this system. Also here they have given that this is frictionless this one. surface, so there will not be any friction between M1 and ground as M2 as well as ground, so there will not be any friction, so you don't have to consider that one. That is what it has been mentioned. And then there is a spring between X1 and this one, mass 1 and mass 2. Also there is a dashpot having coefficient B between mass 1 and mass 2 and so on. So what we will do here, first we will draw the force equilibrium, this nodal diagram, and then after that we'll write the force equilibrium equation. And once you write the force equilibrium equation, next step is to find out the transfer function x2s by f of s. Now what is the, okay, for this problem what I said that first you have to identify how many nodes are there. So number of nodes will be equal to number of displacement points. So in this given diagram, there are two displacement points. One is x1t and another one is x2t. So we have to draw two nodes, x1t and another one x2t, and one more node as a reference node, right? So see that here, okay, here I think I have not given the solution of this one, but you can write x1t and x2t as a node. Then what you have to do, one for x1t, that node, this f of t is you have to connect. So force, one end of force is connected to x1 and another one is to the ground. Then mass will be connected between x1 and the ground. Then this spring will be connected between x1 and x2, and then dashpot will be connected between x1 and x2, and then after that this mass will be connected between x2 and the ground. So you have to, okay, this network diagram and then a nodal diagram, and then after that you have to apply the force equilibrium equation at node x1 as well as at node x2. So you get two equations, and then from that you have to take the Laplace transform, and then finally you have to find out the transfer function. So in that way this problem can be solved, right? Now suppose for example this is the given example that this is the reference one, right? So one end of the spring is connected to the reference, another one is connected to M1, and then this mass element force is applied here. So this is displacement point x1, then this B3 is the dashpot between M1 and M2, then x2 is another displacement point, and then B4 is basically this dashpot between M2 and reference 1. Also, they have mentioned that there is a friction between mass 1 and the ground, so that is given by a B1. So friction is always represented by dashpot. Also, there is a friction between M2 and ground, so that is given by B2. So you can represent that as a dashpot here, also here dashpot. So what you have to, first thing is that you have to draw the nodal diagram. So in that nodal diagram, how many nodes are there? X1, number of nodes, displacement 1 equal to x1 and x2. So you can write one x1 node and x2 node and one more as a ground, right? So see that this x1 and x2 is the this node and this node. Now between x1 and to x1, how many elements are associated? This mass element. So mass element is connected between x1 and ground. Spring element, see that one end of spring element is connected to the x1 because this is the nearest displacement point. So this is connected, this one. But another end of the spring is connected to the ground. So this is connected to the ground. Also, this force is associated with x1. So this force is connected to the x1, and then another end of force is connected to the ground. Then between x1 and x2, there is basically this one. B3. So between x1 and x3, this B3 dashpot is there. But you know that this B1 is the friction associated with this mass element, and then this is nearest to the x1. So this B1 is, and this is since it is referred to the ground. So one end of this B1 is connected to the ground, and another end is connected to x1, right? Then this B2. One end of this B2 is connected to the ground, and another one is nearest displacement point, that is x2. So B3 is also, one end of B3 is connected to x2. One end of this B2 is also connected to the x2. And also this mass elements M2, one end of this one is connected to x2, and another end of this is connected to the ground. Now see, look for this B4. One end of this one is connected to the nearest displacement point, that is x2, and another one is connected to the ground. So that's why it is connected to the ground. So this is the overall nodal diagram of given mechanical system. So how many nodes are there? There are two nodes, x1 and x2, right? So and then these are the associated elements which are connected in this fashion. Now you can apply incoming force, means a force equilibrium equation at node x1. Also you can write the force equilibrium equation at node x2, and then once you write the force equilibrium equation, you can take the Laplace transform, find out the transfer function. Suppose, for example, if x2 is output, then x2s by f of s will be the transfer function. So like that way. So in that way you can find out. Now see that, like in this example 8, find the transfer function of a mechanical translational system in okay, of given figure, this one. Now see that this is okay, reference one, and then spring element and dashpot, and then mass element is there, and then force is applied in this direction, in the downward direction. So definitely there will be opposite upward force offered by this mass element as well as spring element and this one. So this is the force free body diagram, and then if ft is in downward, force offered by this mass element will be in upward direction, force offered by this spring element will be in upward direction, and force offered by this dashpot element will be in upward direction. So as per force equilibrium equation, Ft will be equal to total applied force must be equal to total reactive force, that is Fk plus Fm plus Fb, and then you know that Fk is associated with K into x of t plus this Fb is associated with K B into d xt by dt, and then Fm is associated with m into d2 x of t by dt square. So if you take the Laplace transform of that equation, and then if x of s is the output and f of s is the input, then this will be the transfer function of that system by solving the equations and so on. Okay, then these are some more examples. Restaurant plate dispenser, so that we can also find out the transfer function of that one. Then, like for example, this is a 10th example, and if somebody asks you that find out the transfer function of this system when x2 is considered as the output and f of s is the input, where is the f of s? Here. And then this is the output, and then this mechanical system is given to you. So from that you can draw the free body diagram, or you can draw the nodal diagram. So free body diagram for this one is what? See, for this one, Ft is the force in downward direction. So there will be definitely Fm2 will be the force in the upward direction. And then if you press this one down, so definitely K2 will be in upward direction. Also there will be K1 in upward direction. Fb will be in upward direction. So this is the force associated with M2. Then what about M1? See that when it is Fk1 is in upward direction, Fb is in upward direction, and then Fm1 will be also in upward direction. So you have this free body diagram, so you can apply this one equation for this one. So what will be this one? Total incoming force must be equal to total outgoing force. So that is equal to Ft is equal to Fk1 plus Fk2 plus Fm2 plus Fv. And then for this diagram, so this total force must be equal to 0. So you got this one. Okay. Then you can find out the Laplace transform of given problem, and then finally x2s by f of s. So that will give you the transfer function of that system. Then this one, see that this is another example, and okay, you can also solve this example by using the nodal diagram, and you can do the practice of that one by finding the transfer function. Like for example, you can take the x3 as the output, and then okay, in the problem they will mention you that which is the output and which is the input. So definitely input is your t, that is nothing but force input, and the output is the displacement. So either you can take the x2 as the output, or x3 as the output, or x1 as the output, depends upon the given problem, and then we can find out the overall transfer function of a translational mechanical system. So this finishes the translational mechanical system. In our next lecture, we'll study the rotational mechanical system, and then how to draw the free body diagram, how to draw the nodal diagram, how to find out the nodal equations, and then overall transfer functions, and so on. So we'll stop here, and I say that this translational mechanical system is over now, right? So if you have any doubt, I'll be happy to answer the questions.